Okay, everybody, welcome back. Today's lecture begins kind of the end. The next four lectures of so the next four lectures are going to cover basically the same topic. At the end, so in a couple days, or maybe even probably not by the end of lecture today, but during lecture tomorrow, I'll start on what is truly the last topic. What's going on here is that we're now going to be kind of repeating the thing that we did in chapter 1 for first order equations to first order systems. And so ultimately, we're going to look at first order linear systems here today, and then we're going to apply what we figure out today in terms of what's called the classification of phase portraits for these linear planar systems. And we're going to see how that applies to slightly more general equations that are not linear. Okay, so that's the big thing. We'll see how all of this works. Okay, so let me start by saying what we're talking about now: linear planar systems. So, as mentioned in last lecture, the idea is to look at these 2 by 2 systems. So I'm going to relabel them slightly. Rather than using x1 and x2 as the components, I'm going to use x and y as the components. So our linear planar systems look like this. So I have ddt of x of t, y of t, and this is matrix A times solution vector x, y. Okay, where A is our generic 2 by 2 matrix, A11, A12, A21, and A22. Okay, so rewriting this slightly, this is the equation, right? ddt of x of t, y of t, which is matrix A1, A1, or sorry, A11, A12, A21, A22 times x1, or sorry, x, y. Okay. All right, so this is just a 2 by 2 case that we have spent the last few lectures talking about. I've just relabeled the components of the solution vector. Instead of x1, x2, this is xy. And that's to stress that a solution to this, right, a solution to this is thought of as parametric curve. We know that we can identify a vector xy with points, right, in the plane. So these points depend on t. This is actually a parametric curve with ordered pair given by these two functions of t, xt, y of t, thought of as a parametric curve, right, that traces out a trajectory in the plane. So maybe this trajectory is closed, right? It's like an orbit, right? So you can think of like an ellipse or circle or just some other nice closed curve. Maybe it's not closed. Maybe it's some thing that goes off to infinity at both ends. Okay. The idea is this is some curve in the plane. This is going to be nice because actually this is like exactly what motivates us to study this from this angle, where we're going to be thinking very graphically here about trying to represent the solutions in a more graphical sense, that is, as a bunch of trajectories in the plane. So I mentioned this a little bit last time. How many trajectories do I get? Well, there's a fact that each point in the plane has exactly one trajectory passing through it. Has exactly one trajectory. These are also called orbits. passing through it. Now, the fact that it has a trajectory passing through it, that's the existence part of existence and uniqueness. The fact that it's exactly one and not more is the uniqueness part. The proof of this, which is not really much of a proof because I'm just stating some other thing that I didn't prove, this is from existence and uniqueness. And for that reason, for some given system, what this picture might look like if I try to sketch, of course, since every single point in the plane has exactly one trajectory passing through it, what this means is that sketching all of them, right, is not going to be possible. But we're used to that from the earlier cases of, first and second order equations, especially first order equations. We know we can't draw all of them. There's an infinite family of those things, so I'm not expecting to draw all of them. Even if I could draw all of them, it would just be the entire plane covered in these trajectories, right? So you wouldn't be able to see anything. The idea is that I'm going to draw a few to see what it is that's going on here. What would that possibly look like, right? Well, maybe it would look something like this. Maybe there's a few, right? So there's a bunch of trajectories that don't touch or cross or intersect. That's why, right, this thing I said before, they don't touch or cross one another. There's no intersection points here. That is, again, from this fact. There's exactly one trajectory passing through each point. If two trajectories kind of intersected, right, like here, through that point, there would be two different trajectories passing through that would not satisfy this condition, so that can't happen. Something like this can't happen. Okay, so another example is maybe I have parametric lines like this, and then I have paths that look like this. And maybe there's another path. And if you say what trajectory passes through that point, well, it would have to be something that looks like this, right? Something that can't cross any of these paths that I've already established here, right? And maybe here there's something that looks like this. All right, we're just drawing random stuff. Maybe that's what it looks like. Okay. So this might be another picture, right, that doesn't fail to satisfy this. Okay. Now, what are the solutions, right? Well, we've exhaustively solved this, right? So the solution is always in terms of this matrix exponential, right? So x of t, y of t can be written as matrix exponential e to the ta times my initial vector, right? We'll say x sub I, y sub I, where so this is my unique solution to IVP, where I have initial values, right? X of 0, y of 0 is equal to x I, y I. Okay, so I actually know what my solution is. It's entirely determined by this matrix exponential. Now, what was the matrix exponential for this problem? Well, it depended on this matrix, right? It depended on what the eigenvalues were for that matrix. So the form this solution takes, right? We spent all this effort up till now actually figuring out what the solution is. So unlike in our case way back in chapter 1 when we're trying to do this graphical method, we weren't able to solve most of those autonomous equations. So this was a very rough sketch. Here, we're actually able to solve all of these linear systems like this, right? We can actually explicitly write out the solution for any single linear system that looks like this. And that thing is just matrix exponential times this, where matrix exponential is using the eigenmethods, right, approach. We know what this thing has to be. All right, so by eigenmethods, for any A, which is a 2 by 2 matrix, I'm a little bit off the page. We can find the form of e to the ta, or really this is kind of weird word. I mean, we can't just find the form of e to the ta. We could find e to the ta, right? We can find this matrix exponential. Okay. This depends on three cases, right? Or maybe I should say better, this breaks into three cases, right? So, case one, I don't even know what these cases are. Case one, A has distinct real eigenvalues. Case two, A has distinct complex eigenvalues. In case three, A has one real eigenvalue of multiplicity 2. Those are our very familiar three cases, right, for how we know that the characteristic polynomial of A is a quadratic, so these are the only three cases. Okay. And so, let's focus on the first case. So we are going to look at eigensolution orbits for this one. So let's just look at this first case first, okay? So eigensolution orbits, these are just the trajectories traced by those solutions, which are these eigensolutions. Okay. All right. So, what do we do? Let's say we're in case one. So say we're in case one for problem. We'll write it as x of t, y of t prime is equal to a times x of t, y of t for some given initial conditions I'm not going to write out. And let's say A has, I'm just going to pick one of the eigenvalues, but let's say A has eigenvalues lambda 1, lambda 2 that are both real and distinct. So lambda 1 is not equal to lambda 2. Okay. Well, what do I want to note first of all? Okay. Note firstly that if I take the trivial solution vector, and what I mean by trivial is that they're not just equal to 0 at some t, they're identically equal to the 0 vector. Okay. Note that this is always a solution to, I'll write it as x prime is equal to ax. Okay. Now, this is an example of what's called a stationary solution. Now, remember, we already have this terminology from back in chapter 1. We called these stationary solutions, stationary points, equilibrium points. This is the terminology we used. You'll see later it actually makes sense to also call these critical points. And I'll discuss a bit later the context in which that makes sense. Okay. All right. What this means, of course, stationary solution is that i.e. this solution does not move, right? This trajectory does not move, right? Maybe I shouldn't even call it trajectory, right? Once it's there, it stays there, right? So it does not move. It means that at that point, the trajectory or the path traced out is simply that point, right? For all t, it doesn't move. Okay, that trajectory doesn't trace out anything, it simply remains at that point. Okay, and so another way of writing this is, or saying this, is that the origin is a stationary solution to this. So i.e. The origin is a stationary solution for this problem. And that's always going to be true. Okay. So then let's see what happens off the origin, right? So let my solution x of t be one of the eigensolutions. i.e., if I have an eigenpair, right? If lambda 1 v1 is an eigenpair for A, then we know that this solution takes the form of, this is some scalar c, so some scalar c, I'll call it c1, e to the lambda 1 t v1, right, where c is some scalar, where c1 is some non-zero scalar. Why can we say C1 is allowed to be a non-zero scalar? Because we've already taken care of the C1 equals 0 case when we talked about the stationary solution that's just the origin. All right, so if C1 were equal to 0, then what you get here is your trivial solution. Okay, so let's consider this thing. What's the behavior of this, right? So what is this tracing out? Well, for what is it that's really going on here? What is this path? What is this trajectory? Well, for fixed C1, lambda 1, and V1, right? I let this thing vary over t. Well, as this thing varies over t, what is this ultimately? Ultimately, this is a constant or a scalar, right? At each t value, right? So for a fixed t, this is some scalar times the vector v1. For some other t, it's some other scalar times the vector v1. And so this trajectory is just a line determined by v1, right? This trajectory traces out a line determined by v1. Okay, and so I can draw a picture of this line. There's my line. Actually, I don't want to add arrows to it. I'm biasing the results here, even though this is how it's going to work in my first case. I'm biasing the results a little bit, but let's go ahead and see what happens here. So the behavior of solutions along this line depends on the sign of lambda. So there are three cases. What about if lambda 1 is greater than 0? Here is 0, my stationary point. Okay, so there's 0. To the right of 0, so this is a fixed vector v1 determining this line. C1 doesn't matter here. Here, what matters in what direction I'm going is if lambda 1 is positive, then when t is positive, then I'm going to be moving away from 0, say in this direction. So I have direction away from 0 when t is positive. When t is negative, I have motion in the opposite direction. And so that is what I get. What do I mean by that? It means if I begin, my initial point lies here, not at 0, so my initial point lies here. Instead, then as t goes to, if lambda is positive, then as t goes to positive infinity, I'm going along this line. So this line is my trajectory, going along this line away from 0, okay, to the right. Here, the opposite thing happens. So now, lambda 1 is still positive, but t is negative, and so I'm going away from 0 in the other direction. Okay, all other things fixed. Okay, so what this does is, this line, right, you might say, wait, 0 is a trajectory, but then you have this part of the line, like the half line here, and then the half line here. Don't these intersect? Well, no, because these trajectories, I've drawn them this way as kind of a shorthand, but really these trajectories are, I have this half of the line, which does not include that point. That's a parenthesis, right? That's showing you it's open. It's half open, right? And then I have this other half line, which does not include that point. So that's also a half line. And then I have this point itself, which fills in that line, but technically this is a different trajectory. So this thing about them not intersecting still holds true, but I've drawn them, right? I've drawn them as one single line, even though they're not. They're not really one trajectory, they're actually three. So there's the left half, there's the right half, and then there's the middle hole filled in by the trajectory, which is just a single point. Okay, so this is the reason I'm, belaboring this point is when you draw these pictures that are coming up, this will make it clear that you're not violating the existence and uniqueness condition thing where none of these trajectories are allowed to intersect, because it will look like in the center of the picture, for this case that I'm going to do, it will look like they're very much intersecting when they're not, and this is the reason why they're not actually intersecting. Okay. All right, so that's how that works. What about if lambda 1 is negative? So I have the same line. All right, here's 0. But now what's going on? Right? Remember my eigensolution, I took it off, but my eigensolution is C1 e to the lambda 1 t v1. Okay. Oh, I didn't write lambda 1, so there it is, lambda 1 t. So if lambda 1 is negative now, well then as t is positive, what's going on here? So lambda 1's negative. As t is positive, what's going on? I'm moving towards 0. Moving towards the stationary point. Okay. What about in the other case when t is negative? Well, when t is negative, I'm moving in the opposite direction here, which also moves me towards the origin. And so this is what I end up with. Again, this is actually 3 different trajectories. There's the left half of the line, there's the right half of the line, and then there's 0 that fills in the middle. But on both sides of 0, they're moving towards 0. 0 is a stationary point, it's not moving at all. But all the points, if you have an initial point here to the right of 0, you're moving towards 0 along this line. Okay. What about if lambda 1 is just equal to 0? Well, in that case, my eigensolution, of course, still the same thing. It's C1 e to the lambda 1t v1, but this becomes just c1 v1. Well, what does that look like for different values of c? It still looks like a line. Okay, and of course here's 0. But now there's something different going on here. Right, so the way that this looks is that each point here is stationary. So each point on this line is stationary. How do I know that? Well, this final thing actually doesn't depend on t, right? So this doesn't depend on t. So a point here, as t increases, goes to positive infinity or negative infinity, this point does not move. So every single point on this line is a stationary point. Okay. So every single point is a stationary point. And so that's what this thing looks like. So this is a slightly weirder case here, right, where no motion is going on at all along that line. Okay. All right, so let's see an example of how this will work to draw what's called a phase portrait. So now we want to see how we can use this to draw a phase portrait. For some linear system. Okay, so let's do an example. So let's say we have the equation d dt of x of t, y of t, which is a times x, y, where a is 0, 2, 1, 1, times x, y. So there's my a. Okay. I'm going to use Cayley-Hamilton after I find eigenvalues here, so let's just do this quickly. So note, characteristic polynomial of a is z squared minus the trace of a, z plus determinant of a. So this is z squared minus trace of a is 1, so this is minus z plus determinant of a, which is 0, minus 2, so this is minus 2. Oh, this factors pretty easily as z minus 2, z plus 1. All right, so eigenvalues are, we'll say, lambda 1 is minus 1, and lambda 2 is 2. Okay, so let's find eigenvectors for each of these. So to do that, I'm going to use Cayley-Hamilton. So I'm going to look at a minus minus 1i, which is a plus I. Well, a plus I is 1, 2, 1, 2, right? So eigenvector for lambda 2 equals 2 is 1, 1. And a minus 2i is, of course, minus 2, 2, 1, minus 1. Okay, so that implies that an vector for lambda 1 equals minus 1 is, you just take the first column, minus 2, 1. So I have eigenpairs minus 1, minus 2, 1, and 2, 1, 1. Okay, and this is by Cayley Hamilton. So then what are my corresponding eigensolutions? So eigensolutions, what are they? I have x1 of t is, we'll call it c1. Notice I'm including the constant here. That's fine. Normally the constant multiplies x1, but this is fine. We're just including it here. So this is the e to the minus t times minus 2, 1. And x of 2 of t is c2 e to the 2t times 1, 1. Okay. All right. So those are my eigensolutions. Now I want to draw a phase portrait for this thing. So now I want to draw a phase portrait for this system. How am I going to do that? So the idea is, there's my eigensolutions. Okay, and I want to draw first of all, remember when we did this analysis here on the last couple of pages, so this told me what these line solutions, so sometimes eigensolutions of this type where lambda 1 is a real number are called line solutions because they generate a line here. If lambda 1 was positive, this is the picture I got. Lambda 1 is negative, this was the picture I got. And if it was 0, I got this weird picture where all these things are stationary solutions. So what are those lines? Remember, these lines were determined by the eigenvector in question. So what that means is that I have lines determined by, if I'm thinking of in the plane, the vector 1, 1, well, the vector 1, 1 is just this diagonal vector, right, where x and y are equal. So the line determined by 1, 1 is the line y equals x. Right. This is the line y equals x in the plane. Okay, if you like. What is this line? So this vector determines a line minus 2, 1. That vector, so this is my origin, right? This is minus 2, 1. So it's this line. Okay, so this is the line determined by V1. Sorry, this is the line determined by V2 here. So this is determined by, this is, if you like, this, you can think about this line as being CV2, and this line is CV1. Okay. Now, along the line determined by V1, my eigenvalue is negative. It's negative 1. So let's go back to our cases. In the case that the eigenvalue is negative, what that means is that this was the picture I got along that line. Arrows indicating motion towards 0, towards the origin. So on this trajectory, determined by the vector minus 2, 1, so that's this line, I have arrows indicating motion towards the origin. On the other line, determined by the vector 1, 1, so V2, my eigenvalue is positive. That was the first case I handled. And in that case, I get an indicated motion away from 0, and away from the origin. So what is the way of looking at this picture? Well, when, say, C2 is 0, right, and C1 is non-zero, then the solution I get looks like something along this line. It's this line, right? And, of course, at 0, that's when C1 and C2 are both 0. I get the origin and I stay at the origin. But anywhere else, at any other initial point, I get this thing, which moves towards the origin as t goes to infinity, right? So as t goes to infinity, this moves towards the origin here. Okay. Similarly, if C1 is 0 and C2 is non-zero, right, then I get something along this line, right? And of course, if C2 is also 0, I get the origin, and I don't move at all. But if C2 is non-zero, then I get something along this line, so one of these two half lines here, that moves away from the origin as t increases. But what if, and I know this, right? I know my general solution is not something where one of these c's is 0. My general solution, right, looks like this. My general solution looks like c1 e to the minus t times minus 2, 1, plus c2 e to the 2t times 1, 1. So my general solution is a sum of these things. So it's not purely going to lie on one of these lines. If it lies on one of these lines, then it's either this or this, right? So then what does a trajectory that doesn't lie on one of these lines look like? Well, it looks like this. Or it looks like this. Or this. Or this. Now, first, how do I know it looks something like this? Well, I know that it can't touch or cross the other curves that I've already drawn. So the curves that I've already drawn are the point 0, the origin, and the 4 half lines. This half line and its opposite, and this half line and its opposite. Okay, those are the 4 trajectories. Notice that those split the plane into 4 pieces. Right, and these 4 pieces, whatever trajectories I draw in here, they can't actually cross or touch one another, right? So if I drew another trajectory, it would look like this, or this, or this, right? Not allowed to cross or touch any other trajectory that I've drawn. Now, how do I know it looks like this and it's not like a bunch of circles here that don't touch each other? Well, because of continuity arguments, I know that it kind of, as I'm really close to this line, it kind of has to behave very similarly, right? So it has to be almost a lined thing, coming out and out and out and out this line. And then when it gets here, it can't touch 0, so it kind of turns, and then it's a line going out this way, right? That's how I know what this how this has to behave. Because of that, I know what directions I should draw in here on these curves. So I want these curves to behave continuously in the sense that when I move from a curve to a nearby trajectory, the behavior should be very similar, right? It shouldn't behave one way like this and then boom, like flip over to something that's behaving crazy. Right, so that's the continuity argument. And so if I draw in the arrows here indicating the direction as t goes to positive infinity of these trajectories, this is what this looks like. So these are the directions indicated here. And directions look like that. So they're sweeping from this vector out towards, or from this line out towards this other line. Now, what's another way of seeing how this has to go? I can quickly, the notes does this in the next section, which is when we're going to talk about the classification of phase portraits. That's our main goal from this section. So here's what the picture would look like if I drew this all the way. Without this kind of intuitive type of reasoning, we could also figure out how this thing has to go by just taking limits, right? So if I take limits, say, of this thing as t goes to positive infinity, this is going towards the origin. Here, this is if I have this expression, this addition, as t goes to positive infinity, this is going to 0 and this is going to infinity. So it sweeps from this thing towards going off to infinity, right? If t goes to minus infinity, right, going backwards, right, the opposite is true. Okay, I can do the same thing here. So it sweeps from this towards the other, right? Notice the arrow of direction here goes from a direction that aligns with the eigensolution x1, and it sweeps towards aligning with eigensolution x2. That's because as t is going to positive infinity, this x1 eigensolution is going to 0 because it's e to the minus t, and this one's going to infinity, e to the 2t. So this one dominates. This one dominates. Okay, because it's positive and this one's negative. Now we're going to see it splits into a finer thing there. You might say, well, what if both of them are positive? Well, then the larger one dominates, right? What if both of them are negative? Again, the larger one dominates. This example is very important to understand because even though it's kind of the simplest example of this, it still contains basically everything that is required to understand what's going on here. If you want to see a picture of this that is, nicer, but still looks basically the same here, you can look this up. This is on page 6 this is 3.7, I believe. Okay, so it's the linear planar systems section, whatever section of chapter 3 that is. Okay. All right. So that's what's going on. Now, let's get to what it is we're actually interested in from this example. So this example is going to allow us to classify phase portraits in a similar fashion. Or I should say classify all phase portraits by carrying out a similar type of analysis. So basically we want to take the picture that we got from this example and the type of reasoning that we use to generate this picture, and we want to apply it to more to more general cases, or to the other cases, right? So going all the way back here, remember, for a linear planar system, there was 3 cases for the eigenvalues here. 2 distinct real eigenvalues, 2 distinct complex eigenvalues, 1 real eigenvalue with multiplicity 2. Those are the 3 cases. So far, we've really only touched that. First example we did is going to allow us to totally exhaust this case, but then we're going to have to do a little bit more work to get the other 2 cases. Okay. All right. So this leads to our very important thing. Let me get a little bit more paper here. Okay, so this leads us to classification of phase portraits, or phase plane portraits. Okay. In total, there are 20 cases. Okay. These cases, so it's 3 main cases with several subcases each. Okay. All right. If you want to see a description of these things in words, so if you want to see a description of any of these cases in words, look in the YouTube chat. I have posted a link to this section, and you can follow along here. It would take a ridiculous amount of time to actually write out all of the words in each case, so I'm not going to do that. I'm going to draw pictures of how this works. I'm going to do my best to draw nice pictures to show you how these things go. But if you want the description of why those pictures look that way, you're going to have to read all of the words in each case, which, like I said, I'm not going to write out. Okay. So there are 20 total cases. Now it turns out that a lot of those cases are kind of fluff, and they're rare cases and subcases that aren't really going to show up that often. A lot of the other cases are essentially duplicated. So basically, there will be a case and then like an anti-case. You'll see what I mean when I write these things out. And so there's a lot of duplicated info here. It's not 20 completely different cases, but technically it is 20 cases here. 3 major cases that are exactly the 3 cases you expect. So 3 main cases are just what type of eigenvalues you got, right? So 2 distinct real eigenvalues, 2 distinct complex eigenvalues, and then 1 real double eigenvalue, right? Eigenvalue multiplicity 2. Those are the 3 like mega cases, and then each of those cases has subcases, all right? So let's do mega case 1. So mega case 1. 2 distinct real eigenvalues, lambda 1 and lambda 2. Now in this case, the general solution to, I'm going to call the system that we're solving star eternally for the rest of this lecture. The general solution to star is x of t is c1 e to the lambda 1 t v1, where v1 is an eigenvector for lambda 1, plus c2 e to the lambda 2 t v2. Same thing, right? So if you like, I could write these as eigenpairs, right? Maybe I'll do that. So I have eigenpairs in the usual way. Okay, there they are. So then this is my general solution. Every trajectory of this system is just the plot, right, the graph of this thing. So this is a parametric curve. It traces out some trajectory in the plane, and well, it traces out a bunch of trajectories, right? For different choices of C1 and C2, this gives me infinitely many trajectories. Choosing both C1 and C2 to be 0 gives me the origin, right? The point at the origin. Okay. Now, what are the subcases here? You don't need to remember them by number or whatever. Okay, but let's just go through them. So the subcases here. First subcase. You could have a case just like the one we did before. So our previous example was like this. The eigenvalues in question were -1 and 2. So one was positive, one was negative. So maybe that's the case we have, right? Maybe this is what's going on, right? So lambda 1 is negative and lambda 2 is positive. Okay, then the picture we get looks like this. This is called a saddle. Okay, this is called a saddle. All right. So this leads to a saddle. Okay. The next two options, right? Both of them could be negative, or both of them could be positive. Oh, let's do it like this. Okay. What are the other possible configurations, right? One could be 0 and the other negative. One could be 0 and the other positive. Let's see pictures of what these things look like. This is on page 10 of chapter 3.7 if you want to see the pictures. So let's draw the pictures real quick. So the saddle, so this is a little picture of what's going on here. So what does the saddle look like? I have a line determined by vector v1, a line determined by vector v2. Okay, along one of the lines I have motion away from the origin. Along the other line I have motion toward the origin. I have trajectories, right, with motion indicated as I'm drawing these arrows here, sweeping out from one toward the other. Okay. This is my saddle. Why do I keep forgetting the L here? So this is my saddle. And this is the case where one is positive and one is negative. Okay. All right, what's the next? So actually, the next two look very similar. So I get two lines determined by each eigenvalue. What do I know about these lines? Well, since I'm in the case that, say, both are positive or both are negative, so this is the case when we'll say both are negative. So then the arrows are going to indicate motion towards the origin along both lines now, not just along one. Similarly, if I'm in the case that both of them are positive, then along the lines I get motion indicated away from the origin. Okay, what do the other paths look like? Well, they kind of, so here, because we had different directions, right? On one line they're going towards the origin, on the other line they're going away from the origin. So there's some competition here where I'm like traveling along this line and then I sweep towards the other line because the other line starts to dominate. But here, what's going on here, right? Everything is pointing towards the origin, and so a trajectory maybe looks like this. Maybe it looks like this, where it's just coming in towards the origin like this. Maybe another trajectory looks like this, and another trajectory looks like this. Or again, both of these are just coming in towards the origin, right? Again, here's one, comes in toward the origin. Right, here's another one, comes in toward the origin. Okay. So what is this? This is called a nodal sink. before I explain here, let's see what happens in this case. Well, in this case, I have the exact same thing going on. Now, remember, you might say, wait, I thought that none of these trajectories could touch or cross one another, but here it looks like everything is touching at the origin. Remember that the origin is its own separate trajectory. So these trajectories are going in toward the origin, but they don't touch it. The trajectory starts right off the origin, right? The origin itself is its own closed trajectory that's just a single point. Okay. Now here, what does this thing look like? Well, it looks exactly the same as this, with one key difference. All right, so maybe this is what I have going on here. And so, what's the key difference here? Well, now, because the motion indicated is all away from the origin, along these trajectories, the motion is outward. This is called a nodal source. Now, what's the difference between sink and source here? So sink, these trajectories, all this motion indicated is towards this sink, okay, this node, right, this single node that's the origin. Everything is moving towards it. That's why it's sink. Source, everything's moving away from it. It is the source of this motion here, okay. So the difference between sink and source is the direction of the trajectories, whether they're going toward the origin or away from the origin. Okay, so that's those two cases. Next, I have the two cases where one of the eigenvalues is 0. Okay, and so I have the line coming from the non-zero one, okay, and the line coming from the 0 eigenvalue. So this is the case, like I said, we'll say that lambda 1 is less than lambda 2, which is equal to 0. We'll say that lambda 1 is this first one, lambda 2 is the second one, so this is CV2, if you like, is this line. And we'll do the same in the second picture. Actually, we'll change it in the second picture. We'll change it around. So this is 0 is equal to lambda 1 is less than lambda 2. So just so the picture looks the same, we'll arrange the picture so that, which means we just rotate the picture if we need to, so that this is CV1, okay, instead. All right, and so then along the eigenvalue, or the line determined by eigenpair with the 0 eigenvalue, there's no motion, right? It's stationary. All these are stationary points. Along the other eigensolution line, I would get motion toward the origin since it's negative. Okay. Similar here, since I've said that this line in this picture is going to be my stationary line of stationary solutions. Okay, then along the other one, I would get motion away from the origin, since the eigenvalue there is positive. Okay. All right. Okay, then now what? Well, let's see what the other trajectories should look like here. Well, the way that they look is basically so if you're at any of these points, you just stay there forever. Off this line, though, the trajectories I get are just half lines going, in this case, towards these stationary points. Again, I'm drawing them simply by passing through, but they're really half lines, right? One coming from here, one coming from there. And they're going towards these stationary points. Okay. In this picture, it's the same thing except they're half lines emanating from these stationary points, so they're moving away. The same thing here and here. Okay. This is called a spinal sink. And this is called a spinal source. Okay. So that's how those cases work. So this completely exhausts the configuration of two real eigenvalues, right, by trichotomy. The only possible thing is one positive, one negative, both positive, one negative, one zero, one zero, one positive. That's it. Those 5 cases exhaust all possibilities. Okay. Now, this is bringing us to mega case 2. All right, so mega case 1 was 2 distinct real eigenvalues. So then mega case 2 is 2 complex eigenvalues. 2 complex eigenvalues in a conjugate pair. Okay. So these eigenvalues, of course, look like mu plus or minus I nu, right? The eigensolutions then, right, so x of t, this is the general solution, then is the C1 times the real part of e to the mu plus I nu t. I'm just going to write it as lambda t times v plus C2 times the imaginary part of e to the lambda t times v. Okay. All right. Now, recall our equation that this solves looks like this. Okay. Where A is equal to A11, A12, A21, and A22. Now, it turns out that this splits into 6 cases. The possible phase portraits, split into 6 subcases. The subcases, as you might have thought about already, depends on the real part of this eigenvalue and whether it's positive, negative, or 0. Okay, so what are the cases? So actually it splits into 3 cases and 2 subcases each. So 1, mu is 0, and this entry here, A21, is either positive or negative, so A21 is positive. Mu equals 0, and A21 is negative. Now you're going to say, what does A21 have to do with anything here? We'll see. We'll see how this works. The third case is mu is positive, or we'll say mu is negative first, and A21 is positive. The fourth case is mu is positive and A21 is negative. The fifth case is mu is, I should have probably kept these together, that's fine. Mu is negative, A21 is negative. I should have kept these two together. And 6, it's fine. When I draw them, I'll put them together. Mu is positive, A21 is positive. So I did them out of order here, but that's fine. That's the 6 exhaustive cases. Okay. All right. So what is this A21 being positive business? So A21 determines, and you might say, can A21 be 0 here? It's a fact of linear algebra. It's not allowed to be 0 there. If it was allowed to be 0 here, because A has real entries, if this is 0, the eigenvalues have to be the diagonal entries of A. And because of that, you would have real eigenvalues. So it wouldn't be possible to have complex eigenvalues if this thing was 0. So that's why it can't be 0. It's got to be positive or negative. Okay, so this is what you get. So A21 determines the direction, you'll see in a second, of the trajectories by the right-hand rule. So if you don't remember the right-hand rule or you forgot it, okay, what's the right-hand rule? So the right-hand rule in the context of this is if A21 is positive, we take our thumb on our right hand and we point the thumb up. Okay, now when you do that, you let your fingers, okay, curl naturally, right, just in the direction they do. You don't turn your hand or do anything funky like this. You just leave them curling like this. Thumb up, fingers curling like this indicate, so the curling of my fingers indicate direction of motion. They indicate a counterclockwise direction. Okay, so A21 being positive indicates a counterclockwise direction. A21 being negative would be me taking my thumb and now pointing on my right hand and pointing it down. Okay, so down into the paper, letting my fingers curl naturally. They now curl clockwise, right? So A21 positive means counterclockwise. So this is counterclockwise. And A21 negative implies clockwise. Okay. So then what do these pictures look like? So I get two pictures here that are almost identical. This is going to be the case when mu is equal to 0. That is, the real part's equal to 0. And here we'll say A21 is positive. And then we have mu is equal to 0 and A21 is negative. So the origin is again a stationary point. What do the other trajectories look like? I don't get these lines anymore, right? Those lines came from my real eigensolutions, right? Which, like I said, sometimes are called, in the notes, they're called line solutions. So those lines came from my real eigensolutions, but I don't have any real eigensolutions now, right? My only eigensolutions are the complex ones. So what do I get here? I get ellipses. I get ellipses look like this. And since A21 is positive, these are counterclockwise ellipses. So the motion indicated looks like this. So this is a counterclockwise center. These are called centers. Similarly, the picture here is exactly the same, except since A21 is negative, the motion indicated is clockwise. This is a clockwise center. Okay. Next case. So let's do the case when mu is negative. Okay. So let's do mu negative, A21 positive, and mu negative, A21 negative. So again, my origin is stationary point. So what this thing looks like is a spiral. It spirals in like this. Maybe here's another part of the spiral. And I get a clockwise spiral in towards the origin. Or sorry, this is a oh, let's fix this. Rather than redraw the picture, I'm going to just change this. We'll say this is negative in the first one. We'll change this one to be positive. Yeah, there we go. Okay, so this is what this looks like now. This is a clockwise. This is a clockwise spiral sink because it's spiraling into the origin. Here, I am going to also get a sink. It's going to be spiraling into the origin, but it's going to happen in the other direction. So it's going to be a counterclockwise sink. Right, and maybe like the other one looks like something like this. So this is going to be a counterclockwise sink. This is counterclockwise spiral sink. So notice it's a spiral sink in both cases. It's just a question of whether or not it's clockwise or counterclockwise. Okay. Let's do next. What happens when mu is positive? So let's say mu is positive, and I'll keep with the, so mu is positive and A21 is negative, and mu is positive and A21 is positive. Okay, again, the origin's a stationary point. In this case, because mu is positive, I'm going to be spiraling out from this thing. So actually the spiral looks similar to the spiral I drew here, but now I'm spiraling out. Away from the origin, which makes that spiral go clockwise. So this is a clockwise spiral source. Source because I'm moving away from the origin. And lastly, this thing is going to look similar to this, except the arrows are moving in the opposite direction, right? So this thing looks similar to what I got here. Okay, except the arrows are now moving again away from the origin, right? So So this is a counterclockwise spiral source. So this exhausts the complex roots case. So we had 5 total cases coming from the real roots case, 6 coming from the complex case. That's 11 total different phase portraits. But I told you at the beginning there were 20 of these. So the remaining 9 come from the last case, which is one real double root. So the last mega case. Mega case 3. One real eigenvalue with multiplicity 2. Okay. And so, what are the possibilities here? Okay. Well, there's one simple. Okay. So this splits into 2 major cases and many subcases. 9 total. So the 2 major cases that this splits into, I'll call maybe like 1 and 2. So the first one is the thing that doesn't happen very often, but we still have to cover it. So this is A is equal to some mu times the identity, i.e. your matrix A, it turns out, is just mu 0, 0, mu. That can happen, okay? In fact, like this is one easy way to get an eigenvalue that's repeated. And then the second case is A is not equal to that. So not every matrix with repeated eigenvalue is exactly the identity. For instance, you could have 2, 1, 0, 2 that has double eigenvalue lambda equals 2, but it's not equal to the identity. So this is by far the more common of the 2 of these. But let's just do this real quick to get it out of the way. So case 1, A is equal to, here, I'll write it like this. A is equal to mu times the identity. Again, this doesn't come up much, but this splits into 3 cases. So either mu is negative, mu is positive, or mu is 0. Okay. If mu is less than 0, all solutions radially approach the origin as t goes to infinity. If mu is greater than 0, all solutions radially move away from the origin as t goes to infinity. And if mu equals 0, then in this case, A is equal to the 0 matrix. So every point in the plane is a stationary solution. So there's no picture to draw in this case. There's no picture to draw. Why? Well, there's no picture to draw because every single point in the plane is a stationary solution. There are no trajectories. Each point is its own trajectory. Right? So that's another way of writing this. So each point is its own trajectory. So if you want to draw a picture of all the trajectories in the plane, well, it's just all the points in the plane, so there's nothing to draw. Okay. All right. If mu is less than 0, like I said, radially approaches the origin as t goes to infinity. Mu greater than 0 radially moves away from the origin. So let's see what these cases are. So this is called the null case. That's what this is called. It has no picture, and in this course you're not going to be presented with something like this, so you can forget that this case even exists. Okay, what if mu is less than 0, mu greater than 0? So our first case is mu less than 0. I have the origin, which is a stationary point, and these various lines, right, move, all these half lines move towards the origin as t goes to infinity. That's what you get. Okay. This is known as a radial sink. Okay. Let's look at the similar picture when mu is greater than 0. Okay. So what I get is, again, the same thing. Lines now moving away from the origin. Any line you want. This is a radial source. Okay. So we have 6 more cases to cover and we're done. We'll do that tomorrow. We'll finish the remaining 6 cases in the next lecture. All right. Once we have this classification of phase portraits at our disposal, what this means is that we are going to be able to classify the behavior of these trajectories for any kind of system like this. Any of these linear systems, we're going to immediately be able to understand exactly what this thing looks like, what the trajectories of the system look like, okay? So we'll be able to sketch these orbits. This is going to help us immensely with what comes next, which is being able to then sketch the behavior of solutions to systems that are a little nastier, that are nonlinear even. Okay, in some cases. So this is where we're headed with this. But we got to do this stuff first for these linear systems, and then that's going to show us how to apply that to be able to sketch trajectories for much more general systems. So anyway, that is the deal. So I will see you all tomorrow.